Welcome to Spring 2019 weather training from Minneapolis air traffic controllers. Once again this year we're going to be talking about thunderstorms, and topics will include a review of thunderstorm characteristics and hazards. We'll review the TCF and we'll address some weather radar concerns. First, a word about the power of thunderstorms. An experiment known as GRAPES 3 in India was recently devised to study incoming cosmic rays from space. From 2011 till 2014, researchers recorded thunderstorms over ground sensors blocking subatomic particles resulting from these rays. In December of 2014, studying the electric field around one thunderstorm produced an astonishing result. In this monster storm, their calculations indicated that the voltage in the storm was 1.3 billion volts, about 10 times more than the biggest voltage in a thunderstorm measured previously. This equates to more than 2 billion watts of power, which is comparable to a large modern nuclear or hydroelectric plant. The implication is that thunderstorms can become far more powerful than previously thought. In any event, proper avoidance in aviation is, as always, extremely important. So how well do you know thunderstorms? This presentation contains an informal 10-question quiz. If you'd like, but you're not required, stop this module now for a moment and grab a pencil and paper. Keep track of your answers and give yourself a point for each right answer you get during the module. And then at the end of the presentation, add up your points and we'll rate your storm expertise. Here's question 1. On average, how many lightning strikes occur around the world in a given second? The answer is C, 93. That's roughly 8 million lightning strikes every day worldwide. Obviously, thunderstorms are an extremely common weather phenomenon, but familiarity with them may make aviators forget just how much caution is needed when routing through areas of thunderstorms. Let's review the ingredients needed to produce a thunderstorm. There are basically 3: water vapor, unstable air, and a source of lift. How do meteorologists know how much of each ingredient exists for a forecast? Taking a look at water vapor, meteorologists will look at humidity, temperature, dew point spread in different layers of the atmosphere. To determine whether or not there's unstable air, they will look at a vertical temperature and humidity profile and ask the question, are there layers, when pushed, that would continue to rise on their own? The amount of moisture in the atmosphere adds to the instability. The more moisture, the more energy. And then look for the presence of a source of lift, either fronts or troughs, which may produce some dynamic lift. Look at the time of day for possible solar heating, and then look aloft for jet streams that effectively remove air from the top of a thunderstorm. There are basically 3 stages of thunderstorm development and dissipation. There's the towering cumulus stage, the mature stage, and the dissipating stage. In the cumulus stage, that's when we have the cloud development, and it's made up primarily of updrafts, but these can be hazardous and cause turbulence. Expansion is sometimes visible with the naked eye. In the mature stage, ice crystals will appear at the top. You'll get the appearance of an anvil. A rain shaft will appear at the bottom, and updrafts and downdrafts both exist inside the thunderstorm. In the dissipating stage, the cloud takes on a fuzzy appearance. It's made up primarily of downdrafts, and the rain starts to weaken in intensity. It's important to note that a thunderstorm can pass through all 3 of these different stages in as little as 30 minutes. So it's a very dynamic situation with thunderstorms. Things can change very rapidly, and it's important to stay on top of thunderstorm activity. So here's question 2. Routing under the anvil of a large mature thunderstorm will allow relatively smooth rides and the avoidance of hail. Is that true or false?
Sands, you need some help?
The answer is false. If you want to experience severe to extreme turbulence and expose yourself to hail damage, then try flying under a thunderstorm anvil. CB anvils are notorious areas of bumpy air, and an encounter with hail is possible under an anvil even several miles from the main thunderstorm shaft. Avoid flying, or if you are a controller, routing aircraft near or under a known anvil top. Now let's explore the different types of thunderstorms. The first type is the single-cell thunderstorm. It consists of a single main updraft that is quickly replaced by a downdraft once precipitation begins. Single-cell thunderstorms are usually short-lived, are alive for probably less than 30 minutes, and the majority of single-cell thunderstorms are sun-driven. Sometimes they are referred to as pulse, popcorn, or air mass thunderstorms in the absence of strong fronts. They are most frequent during the late summer and late afternoon and early evening in the Minneapolis region. The problem with single-cell thunderstorms is that the precise locations of isolated air mass development, like near an airport, are hard to predict. Obviously, their timing and location can be critical to traffic. Air mass development can get complicated when outflows from single cells interact with other outflows in cells, as you can see in this example. Unorganized development like this near Chicago is often not well forecast hours in advance by models. So single-cell thunderstorms is sometimes one of the more daunting forecast challenges that meteorologists have in aviation. The second type is the multi-cell thunderstorm. These usually occur along a front or an outflow boundary and can last for hours. The individual cells mature and are carried downstream by upper winds, and the new cells form upwind from the previous cells and take their place. Cell movement may actually be different than area or line movement. The cell moves forward, but the area of lift, where you've got thunderstorm formation, may be shifting more slowly. So when someone like a pilot asks, how fast are those thunderstorms moving? The answer can often be given in two different ways, as a cell or an area or line movement. Here's an extreme example. Something called training echoes. When the lifting process is shifting very slowly or stationary, training echoes may occur. Each of the thunderstorms follow the path of the preceding storm. The cells move, but the area does not. This can create large rainfall amounts over a short period in a smaller area, which may lead to flash floods. It's also tough on air traffic management for obvious reasons. Multi-cells can also produce squall lines. When the area of lift is shifting rapidly, TS may form in a line which can extend laterally for hundreds of miles. These squall lines can persist and move for many hours and produce damaging winds and hail. Gust fronts or damaging straight-line winds are common from squall lines. Here in Minneapolis, multi-cells and squall lines are most common in the late spring and early summer months. The third type of thunderstorm is the supercell. It's the main source of severe weather, and updraft speeds in a supercell can exceed 9,000 feet per minute, or 100 miles per hour. Supercells can be found in multi-cell clusters and lines. So what defines a supercell? The instability and lift is so strong in a supercell that the cell develops its own rotating mesoscale circulation. It's sort of like a miniature low-pressure system. The rotation of the storm may actually be visible to the naked eye, and hence you have extreme wind shears and extensive turbulence with a supercell. Normally, supercells will have very high tops, usually greater than 45,000 feet. The final type of thunderstorm that we're going to cover is called the nocturnal thunderstorm. These are very common in Minneapolis in the summer months, and they correspond to the strengthening of the low-level jet over the Great Plains. With low pressure over the Rockies and high pressure in the east, the moist flow increases from the Gulf of Mexico over the plains, and after sundown, winds increase rapidly from 1,000 feet to 5,000 feet above ground level, above what we call the nighttime inversion. This can result in increasing instability and the development of nocturnal thunderstorms over the plains. Sometimes they will develop into what we call an MCS, or a mesoscale convective system. It's a large broken area of multiple cells covering hundreds of miles. The low-level jet weakens after sunrise, which slows the moisture transport, and eventually the system weakens. These systems can produce severe weather and large wind shears at flight altitudes, resulting in moderate to severe turbulence around their periphery, mostly on the north and east sides. Normally, these systems weaken rapidly after sunrise, but they can often foreshadow additional thunderstorm activity in the same region later in the day. So here's question 3. Severe low-level wind shear and turbulence are not a problem with isolated single-cell or air mass thunderstorms. Is this true or false? The answer is false. Low-level wind shear, gust fronts, or microbursts may be found under small or any thunderstorm. One prime example are the dry microbursts that occur in arid conditions, typically found in the western U.S. with small cells, and these can be extremely hazardous to fly into. Flying under a thunderstorm in these conditions could cause loss of control of an aircraft and result in a fatal accident. Yet these cells may appear fairly weak on the radar. So, to review thunderstorm hazards, you should understand that these hazards can be found with any thunderstorm: hail, low-level wind shear in the form of microbursts or gust fronts, lightning, icing, and turbulence. First, let's look at hail. Hail is associated with sustained updrafts in the front part of a thunderstorm, and they most frequently occur with multicell or supercell type storms. It's important to note that hail can often be found aloft but not at the surface. Hail can be encountered in clear air several miles from thunderstorm clouds, such as under blow-off or anvil tops. Hail can also fall as fast as 100 miles per hour. And states with the highest hail risk do include western and southern sections of the Minneapolis area. The second thunderstorm hazard is low-level wind shear. Wind shears, or abrupt changes in wind direction and or speed, may occur at any altitude in the atmosphere, but they're most dangerous near the surface. Low-level wind shear is defined as a change of wind speed of 10 knots or more per 100 feet in a layer more than 200 feet thick, which occurs within 2,000 feet of the surface. Severe low-level wind shear is an airspeed loss or gain of at least 15 knots and or altitude loss of 500 feet per minute. So here's question 4. At the surface, a microburst is an area of diverging winds, converging winds, upward air motion, or no winds or motion. The answer is A. A microburst is an area of diverging winds at or near the surface, and they cover an area of less than 2.5 miles along a side with peak winds as high as 170 miles per hour that last 2 to 5 minutes. Generally, an aircraft flying into a microburst will tend to A. Gain airspeed or abruptly lose airspeed, or B. Lose airspeed and then abruptly gain airspeed, be lifted into the cloud, or finally, D. Be deflected away from the cloud. Which is it? The answer is A. An aircraft will increase its airspeed upon initial encounter with a microburst, but then lose airspeed and altitude abruptly in the center of the downdraft. The shears in a microburst are extreme. A plane may literally be pushed to the ground with a 45-knot headwind that switches to a 45-knot tailwind within a few seconds. That's a total of a 90-knot shear. There is simply no piloting technique that will allow recovery out of many microburst situations, and that is why microbursts must be avoided. Another form of low-level wind shear that occurs with a thunderstorm is called a gust front. A gust front is the leading edge of cool air rushing down and out from a thunderstorm. The edge of the gust front is known as an outflow boundary, and the abrupt wind shift may occur actually miles away from the parent cell. A gust front is an area of converging winds at or near the surface, as opposed to a microburst, which is actually an area of diverging winds. The wind shears with a gust front are usually less critical than the microburst, but they still may be a zone of severe turbulence and cause dangerous overshooting of the runway. The next hazard we're going to look at is lightning. Most lightning strikes do not cause damage. The current is directed along the outside skin of an aircraft. If damage does occur, it's usually minor and can include outside punctures, damage to the aircraft's electronics, or damage to the navigational equipment. One important thing to note is airlines must inspect aircraft after a lightning strike, and this causes flight delays with or without damage, which can run into significant amounts of money. Also, aircraft can frequently induce lightning strikes. The lack of observed lightning with high-topped echoes may not mean no lightning for a flight approaching a cell. So here's question 6. Most severe icing inside a thunderstorm cloud occurs in the anvil blow-off, in the rain shaft, between 0 and minus 15, or between minus 15 and 25 degrees Celsius. The answer is C. In a thunderstorm, abundant supercooled liquid water droplets are present above the freezing level, mostly between 0 and minus 15 degrees. SLD freeze on impact with aircraft. Clear icing accumulation may be very rapid with SLD present. At high levels in a thunderstorm, icing from smaller droplets may be rime or mixed rime and clear. It's important to remember that virtually any thunderstorm will contain severe icing conditions somewhere in the cloud. Here's question 7. To avoid thunderstorm turbulence, the best route for a plane to take around a cell would be A. Over the top of a cell, B. On the upwind side, C. On the downwind side, or D. Under the cell. The answer is B. Downwind areas contain the most extensive turbulence. Recognizing that it's not always possible to route safely on the upwind side, if routing downwind, a rule of thumb some pilots use is to avoid the cell by 1 nautical mile per each knot of wind at flight level. A 60-knot wind would mean a minimum distance of 60 nautical miles downwind. On the upwind and other sides, the area within 5 miles of a cell is worth avoiding, sometimes a greater distance depending upon altitude and PIREPS. A minimum 20 nautical miles is often recommended above flight level 20,000 when penetrating an area between cells. Here's question 8. The Traffic Flow Management Convective Forecast, or what is known as the TCF, graphically shows areas of thunderstorms containing, at a minimum, A. Echotops above 25,000, B. Echotops above 25,000 in at least 25% of the area, C. Echotops above 30,000, or D. Echotops above 30,000 in at least 25% of the area. The answer is B. Areas of convection in a TCF can include an area of convection cells containing at a minimum A. Composite radar reflectivity of at least 40 dBz, echotops at or above flight level 25,000, coverage of A and B of at least 25% of the polygon area, and finally forecaster confidence of at least 50% that criteria A, B, and C will be met. Medium coverage areas on the TCF must contain at least 40% coverage, and lines must contain at least 75% coverage. The TCF is a high-confidence collaborative forecast. It is the primary tool used by ATM to initiate, amend, and terminate planned or active traffic flow management initiatives. AWC, CWSUs, and airline meteorologists have input into the TCF. It's published between March 1st and October 31st, and 4, 6, and 8-hour forecasts are updated and posted every 2 hours. The TCF, however, does not contain all possible areas of thunderstorms. Isolated or low-topped storm cells will not appear on the TCF. Low confidence areas of possible thunderstorms also will not appear. And between October 31st and March 1st, it's a completely automated product. Here's question 9. Anomalous propagation, or what we call false echoes, is filtered out of the warp radar display. True or false? The answer is false. Known ground clutter patterns are filtered out. However, AP is still a problem for NEXRAD, the National Weather Service radar, which is the system that warp and other radar displays use. However, AP is generally easy to recognize because of the random non-contoured patterns and the lack of movement. Wind farm interference, where the false echoes may be contoured and have a closed cell appearance, are less recognizable. It's important then to be familiar with wind farm locations. Echoes do not move from wind farms, and you need to compare those with surrounding echoes. Wind farm interference is often not seen in the absence of AP producing inversions if the wind farms, as in the Minneapolis case, are far enough away. If you have AP, you may also see wind farm echoes. Here's a map that shows the wind farm locations in and around the Minneapolis control space. You'll notice that we have a fair number to our south of Minneapolis over the Iowa border and further south. And it's also important to stress that each radar does have a certain wind farm pattern that is recognizable. It's important to familiarize yourself with these different individual radars and note where the wind farms are located. Here's question 10. Which weather hazard category is responsible for the most accidents to Part 121 or commercial aircraft? A. Ceilings or visibility, B. Icing, C. Turbulence and convection, or D. Terminal crosswinds. The answer is C. In a 96 to 2006 study, the ratio of accidents from turbulence and convection to total weather-related accidents for commercial aircraft ranged from 65% to 94% in any given year. So by far, thunderstorms and turbulence are the most important hazards to the majority of the flying public, including passengers. The greatest opportunity for reducing injury and fatalities lies with programs that reduce the impact from turbulence and convection. As a controller, you have an important role in helping aircraft avoid encounters with thunderstorms, but also the turbulence and wind shears they cause. Keep on top of developing thunderstorm situations and pay attention to locations of reported turbulence and other hazards around thunderstorms to properly advise pilots on routes and altitudes. So how storm-wise are you? If you got 8 to 10 right answers, congratulations, you have earned Supercell status. If you got 6 to 7, not bad, but as a developing thunderstorm expert, you could use some lift. 4 to 5, you're not even off the ground yet, and less than 4, you're still in a fog. Thanks for your attention.